Hello there. Hopefully everyone can hear us okay. Welcome to GeoEngineers' Pipeline webinar series. We're excited to have you join us for our latest episode, Slip Sliding Away. Before I introduce our presenters and a couple quick announcements, just a reminder to mute yourself so that way there isn't any feedback as we're going through this. As a reminder, we're also hosting these webinars quarterly and are always looking for topics to discuss, so please send your ideas to anyone at GeoEngineers. And if you were forwarded the invite or want to add a colleague to our email list regarding future events, definitely let us know. We'd love to get them on that list. Following this webinar, we will also be sending out a certificate of completion. As you can see on your screen here, you can self-report those education credits, as well as a link to a recording of today's webinar. So if you want to watch it a couple times, it'll be in your back pocket to watch. And during today's webinar, if you have any questions, definitely put them in the Zoom chat. During their discussion, I'll be able to chime in and ask those questions, so it's more of a discussion versus just presentation throughout. You can also reach out to us after the webinar today, and we'd love to have a discussion about anything you're curious on that was shared from either Trevor or Andy. So it's now my pleasure to, let me see if I can get their pictures up here so you can get a good picture. So it's now my pleasure to introduce you to two of my awesome colleagues, Trevor Hoyles and Andy Caneday. Trevor is a principal geotechnical engineer with over 23 years of experience. His expertise includes geotechnical pipeline routing, design and construction, as well as landslide identification, avoidance, and mitigation. In his free time, he loves mountain biking with his boys. Andy is an associate engineering geologist with over 22 years of experience. He is a landslide expert specializing in engineering geological mapping, subsurface characterization, and soil and rock slope stability. When he's not working on awesome projects across the country, he loves going fishing, particularly in Alaska. So with that, Trevor, I'll toss it over to you for our safety moment.
All right, thanks, April, and thanks everybody for joining us. I'm going to see if I can go ahead and share my screen.
And you might adjust your audio just a little bit so we can hear you a little bit better.
Okay, is that better?
A little bit. Are people, yes, yeah.
Okay. All right, so let me get back to our safety slide. Okay, so we're going to start off our safety moment with kind of the creepy crawlies. It's spring and it is tick season. So for those that are out doing field work, be aware that ticks are a significant hazard. And the CDC recommends that you treat your clothing and gear with permethrin before you go out. And then when you come back in from the field, try to do an inspection of your clothes and gear before you come inside your home. But then after you come in, it's recommended that you get those field clothes off and get them in the washer and dryer as soon as possible. Take a shower and then do a self-inspection afterwards, and checking particularly where you have hair and where they can hide, and make sure you get those off. If for some reason you do find one that has latched on and bitten, keep an eye out for that telltale bullseye mark. If that does arise, then you should probably go see a doctor and get tested. So anyway, that's the safety moment. Hopefully everybody stays clear of ticks this season. All right, so launching into our agenda, what we're going to do is talk about, in general, just broad landslide classification and attributes, big picture on what landslides look like and their features. Then we're going to get into risk management for new pipelines, the kind of due diligence that should be done at the desktop study level, field reconnaissance and ground truthing. And then routing. Routing is an important part of risk management. And then we'll get into some of the topics of geotechnical evaluation that should be completed as part of a new pipeline project. And then we'll sum it up with some takeaways. So one thing I wanted to point out before we really launch into this, you know, typically on pipeline projects, people think about landslide mitigation. They're thinking about avoiding or mitigating against large, naturally occurring, deep-seated landslides, like the one you see here. Maybe a little bit less obvious than that, but that typically is what a lot of folks have on their mind. But the focus that I really want to have on this presentation is an aspect that oftentimes is overlooked in my experience, and also in my experience tends to affect pipeline owners and operators more so than the large, dramatic, deep-seated landslides, and that's those that are associated with the constructed slopes that comes along with the pipeline construction. If you don't get that pipeline right away restored properly, it can be a real headache to try and come back and fix that stuff, and it also can be a hazard to the pipeline. So we aren't going to get into the details of while it is serious and is a risk to pipelines, big, large, naturally occurring landslides. We're not going to get into the details of stabilizing those or managing pipeline risk within large landslides, but rather we're going to focus on more of the constructed pipeline right-of-way in this presentation. So with that said, I'm going to hand it over to Andy to go over sort of the general landslide classification and overview of landslides in general.
Thanks, Trevor. I'm just going to try to figure out how to share my screen real quick here. Okay. There we go. All right. Can everybody see that? All right. So yeah, as Trevor mentioned, I'm just going to give you a really brief overview of landslide classification, mainly so that you know what you're looking for and can avoid it. That's really our goal here. So what's a landslide? Landslide, in very simple terms, is downslope movement of soil or rock material. We typically classify these things by three characteristics: the activity level, the type of movement, and then what is being moved, whether it's soil or rock or slurry of soil and water. So what typically causes landslides? The big one is water, whether that's surface water, groundwater, snow melt, or in the constructed environment, it's that change in drainage patterns, whether you're diverting surface water and concentrating it, or you're disrupting the natural groundwater flow in a soil. Water is often always there where a landslide is. Other factors include slope steepness, the geology, whether that's material strength properties of that material you're excavating through, or the orientation of rock discontinuities. A big thing we're going to focus on, especially Trevor later in the conversation, is excavation and fill placement. Big causes of landslides are excavating the toe out of an existing landslide, or daylighting a weak soil layer, loading, filling the crown of a slope, or just not properly compacting fill slopes. Other Less common factors can include wildfire, man-induced vibrations such as blasting or volcanic and earthquake activity. So what do we mean when we say the state of activity of a landslide? This is really how active is it? Are we talking about something that's very recent or actively moving, or maybe something like dormant where this is a currently stable landslide that could easily become active by, say, cutting out the toe or changing the water regime in the feature. And then some of the ancient relic features would be those that may have been formed under conditions that are no longer present today, whether glacial activity or mountain building. So geologists love to give about 50 names to everything. Landslides are no exceptions. You know, this is a busy slide, but the key that I want to kind of get across is this idea that we classify landslides based on the type of movement, and that can be falls, topples, slides, spreads, flows, and then what's being moved. And so on the left-hand corner of this graph, you'll see the type of movement, and across the top, you'll see that type of movement that will be, or the type of material that's being moved. So I'll go through some common examples of these landslides, but keep that in mind when you're looking at this, looking at these examples. So the first one is in general kind of rock landslide types that are typical in rock formations, whether that's a fall, just a rock block that's falling due to gravity, or a topple where it's rotating out of the slope, or an avalanche, typical for rock slopes, very large, fast-moving features. Here's a couple examples. You know, rockfall. These are typically associated or a concern for a temporary cut for a pipeline, especially on a side hill where you expose some adverse discontinuities. Avalanches, a little less common, can be found in very steep rocky terrain and tend to be very large, fast-moving features. Rotational slides. This is probably 90% of the landslides that you'll see along a pipeline right away, particularly in the fill slopes. Here's a good example of a rotational landslide. It's actually a much larger, older scarp on the left side of the picture, and then the deposit is reactivated in a secondary rotational slide. Translational slides typically shallower in depth. They can include in both soil and rock, and are associated with a weaker zone of soil or rock on top of a more competent layer. You often get groundwater building up at the boundary between those two layers, and it slides in a more translational motion. Here's a good example of a translational landslide in soil. Typically a relatively shallow compared to a rotational slide, but can pose an equal risk to your pipeline. Here's another example of transitional slide and rock. It's sliding along a very persistent discontinuity or bedding plane in that rock. Debris flows. This is a mixture of soil, rock, trees, and very saturated, flows down a hill, typically has a debris flow track, an area of scouring. And then typically you'll see a fan deposit, much like an alluvial fan, but these are generally created in a single event. The left picture is a typical depositional zone of a debris flow. You can see the large amount of wood debris, rock, this flowed down much like a stream channel. And then on the right, you see the capability for scour on these features. They can, in this case, that's probably 15 to 20 feet of scour created by a debris flow within the channel. Finally, we have a complex landslides, and really all these are landslides where you have two different types of movement, whether that's, in this case, a large rotational landslide at the top that was saturated enough that it could turn into a earth flow, which you see down below on the flats. So why do we care? What's the risk to pipelines from landslide features? Big one is induced strain on the pipeline, whether that's an actual rupture or just bending of the pipeline. You can get loss of ground support underneath the pipeline. And then, as I mentioned, with debris flows, these can scour to a significant debris. So if you're within that scour zone, you can dent, gouge, or scrape the pipe and coating. So now I want to talk a little bit about how we identify these features in the field. There's some pretty characteristic landslide morphology that I'll talk about. And I'm going to use the pretty common example of the rotational slide, because I think that'll probably be what you're most used to seeing along a pipeline alignment. So some of the key features would be the main or head scarp and a rotational slide. This will be an arcuate type feature with a downset blocks of material. And then on the body itself, you tend to see blocks and secondary scarps or cracks. And this is where you also see features like sag ponds and seeps, vegetation changes, and irregular hummocky topography. So I'll show you a few examples of what some of these things look like. Some indicators are very obvious. In this case, we're too late to pick up those indicators. The damage has been done, so to speak. But others are less obvious. In this case, this is a very subtle toe of a translational soil landslide. Very subtle, but as you can see, there's some lobe, the toe bulge on the right of the photograph is a little more obvious. So typically these landslides, they'll start with ground cracking. Seeps will be very common, vegetation changes, and then eventually these will result in displacement of the ground, more substantial displacement, such as this case where we had a developing head scarp. Eventually, as you can see in this photograph, we've got a arcuate head scarp adjacent to a pipeline right away, and then leaning trees on the slide mass as well. Roads are a really excellent indicator of landslide movement. I highly recommend maintenance crews driving the roads and looking for features such as this. The road was not originally constructed this way. This small set down and then a setup is a classic example of ground movement and a really good indication that you've got a landslide. Vegetation, very good indicator. Conifers grow straight. Deciduous trees do not, so they are not as good of indicator. But as I showed on previous slides, you can still see some of that severe leaning on trees. But then also look for vegetation changes, just different types of vegetation, with seeps and hydrophilic vegetation. Sag ponds, these are features you often see at the top of a rotational slide just below the scarp. It's where the downset block is rotated back and creates a low spot where water can pond. very typical for larger rotational features. And then finally, hummocky ground. This kind of LiDAR image, Google Earth image, you can sort of see on either side very smooth topography, and then within the large feature, you get this what we would call hummocky, disturbed ground. So I'll do a quick pause. April, were there any questions that came in on the chat for this section?
Not yet, but if you have questions, definitely post them in the chat. We love it. And yeah, thanks, Andy.
All right, I will move on. Now we're going to move into good practices for risk management on new pipeline construction. So what's a typical scope for a hazard evaluation? Typically, we do a desktop study and then confirm that desktop, what we find in that desktop study with a field reconnaissance, and then perform a routing analysis using all the data we've collected and confirmed, and then finally do a general or site-specific geotechnical evaluation. So what's typically involved in a desktop study? We've two big components. One is to review all the available geologic information. We're not trying to reinvent the wheel. In many cases, a lot of this information is already publicly available. We collect that, sort through it, and confirm its applicability. And then we also use a lot of remote sensing and aerial imagery to such as Google Earth, LiDAR, drone imagery, and InSAR. So I'm going to go through some of these items. So what typically is included in published geologic information? Geologic maps, geologic hazard and landslide mapping, as well as published articles, theses. The image you can see here is publicly available data. This is landslide mapping performed by King County, which is just outside of Seattle. And this is a high-level product, publicly available. You know, if we had a pipeline going through this, you know, we would have a lot less job to do. So it's really good information. Also do aerial photograph interpretation review. This is a great way to determine how the landscape has changed over time. You know, the photographs I show here are, you know, a span 20 years, but the river itself has changed drastically in that time. This is a really good tool for assessing change in the environment. LiDAR is, I would say, probably the single best tool we have for doing assessment of a pipeline alignment. This LiDAR gives you a high resolution ground surface data that can be used for routing and geotechnical design. The great thing about LiDAR is you have the ability to process out buildings and vegetation, and it's relatively inexpensive to perform either a site-specific or an entire alignment. And in many cases, it's publicly available data. So there's a couple examples of how useful this data can be. This is alignment. As you can see, the pipeline alignment cuts through along this corridor, and then right through this, couple landslides really pop out in red. And so this is a great spot to identify and then assess the risk of the pipeline, you know, by assessing the activity level and of these landslides that we mapped. InSAR, another useful tool for collecting deformation time series. This is a radar data collected from satellites. Again, it's a good way of quickly assessing an alignment either during the geologic hazard assessment or as kind of an early warning system for long-term monitoring. The image I show is of a large landslide in Washington State, and this is probably of about 3 to 4 years of monitoring, and the red areas are areas of active movement, slope deformation. So then finally, once you've collected all this information on your desktop study, you want to go out and field truth those areas to confirm the activity level of those features and the risk to the pipeline from those hazards. So with that, I'm going to hand it off to Trevor to talk about routing and geotechnical evaluations.
And Andy, while you're doing that, I'll ask you a quick question that came in.
Yeah.
Is there a typical scour depth of a slide area? And that's kind of a twofold question. And could HDD get below it?
I wouldn't say there's a typical depth for scour. That it's something that can be calculated based on a lot of assumptions, how large the failure is going to be, the steepness of the slope. But it can range from, you know, a couple feet to tens of feet. And then, sorry, what was the second part of the question?
Yeah, could HDD get below it?
Yes, it's something to assess as far as cost-benefit analysis, whether the cost is worth the risk or vice versa. But yes, it can be utilized in those cases. I don't know, Trevor might know if it's ever been used for that, but
yeah, we've done numerous HDDs to get beneath landslides and landslide hazards. So that's fairly common.
Thanks,
All
Trevor.
right, I'm gonna go ahead and share my screen. Okay, so I want to talk about the routing process. This is a really important step in the front end engineering design for a new pipeline. You know, we obviously want to avoid the landslide hazard areas that were potentially identified during the desktop study phase of the project. You're going to save yourself a lot of headaches, obviously, if you can avoid those known hazards right up front in your routing process. The next thing is you really want to minimize side hill orientation of the pipeline. When your pipeline is sitting on a steep slope oriented side hill or parallel to contour, that means a significant amount of earthwork has to be done in order to prepare a level working pad to install the pipeline. And then all of that material has to be put back into place and then remain stable in the long term. So if you can avoid that, that's going to save you a lot of risk and cost in earthwork. So you want to orient your pipeline to the extent that you can with the fall line of the slopes going directly up and down slope, and then potentially staying on ridge lines if you can. By putting in the time and routing your pipeline to the landscape, it's going to save you a lot of hassle in the end. And so I wanted to go over here a comparison of two alternatives that we actually evaluated. On the left in red is a route that fairly clearly was not routed to the landscape. It crosses numerous streams. It's what happened here? It crosses numerous streams. It's on side hills, you know, and that's one other challenge of placing your pipeline on the side of a hill. You're likely to cross a lot of ephemeral drainages and have more issues with water as well. And then on the right, conversely, this route generally follows ridge tops the whole way and avoids all these stream drainages. And when it does have to traverse the slope, it goes straight up and down. So, you know, from a geotechnical perspective and risk management perspective, we would prefer the one on the right, clearly. So I want to talk about the geotechnical considerations that go into the upfront design and construction of a pipeline that's being routed through rugged terrain. As I mentioned, the pipeline orientation relative to the landscape is very important. And even if you've done a great job on routing, certainly there's going to be some areas you just can't avoid. There will be areas that potentially you're going to need to do some cutting and filling as part of the pipeline construction. Those areas would need to be identified during this phase, and potentially recommendations, site-specific recommendations developed for those areas. Another big thing that you need to consider is the water management. A lot of times people see water management as exclusively surface water runoff and use of water bars, which is very, very important. I don't want to understate how important that is, but also water management includes subsurface water and keeping your constructed fill slopes hopefully free of poor water pressures and groundwater that are going to cause instability. And then the specifics with regards to the fill slope construction. As I mentioned, when you cut into the hillside to construct your pipeline, you have to put everything back. Federal and state requirements nowadays require that everything be restored to pre-construction grades. That means if you've excavated, you're going to be building fill slopes. And you know, it's really easy not to construct those properly and have those be affected by instability in the future. And then slope gradient is obviously another key factor to consider in all of this, particularly with the fill slope construction. The steeper the slope is, the more specific you have to be in how it's put back and constructed. Typically, fill slopes constructed at a 2-to-1 or steeper are considered to be engineered fills with a high level of control. So I want to give you all a good understanding of the typical layout of a side hill constructed pipeline. You end up needing a heck of a lot more space than perhaps you would initially think. And it requires a lot of earth moving. And so this photograph or schematic gives a very typical layout for a pipeline construction working surface. And so basically what you have on the right side of the image is your cut into your hill slope. At the base of that, preferably your pipeline ditch is going to be constructed and excavated on the inboard side where you're likely to be in the most stable ground. And then to the left of that, that's your working side where you're going to have your side booms and equipment. And then further left of that is your side cast spoils. That's all your material you've excavated to create this level working bench. And so this is your typical configuration. And I want to go through some other real world examples of what this looks like in the field. So this is again another typical side cut on steep terrain. You'll see on the downslope side here, they've installed timber matting to try to retain those side cast fill soils within the designated right of way. Typically your permitting agencies are not real happy if you start losing your side cast down below your designated construction corridor and right of way. Here's another picture of this side hill right of way. And you can get a sense here of how much earth has to be moved in order to put this pipeline in. Let me show you a little closer picture here. So these are long reach excavators, fairly long, fairly big excavators. And you can see given the scale of this, how large this cut is into the slope. So at the end of all this, you're going to have a 45 foot deep / high fill slope that's constructed here. So it's pretty important that gets put back well. This is an example of an area where it was obvious we were into some natural seeps, some natural groundwater. It was just pouring out of the ground as they started to perform their excavation. So we needed to be prepared with some BMPs more or less for drains to incorporate into this area for the fill restoration so that we didn't have an accumulation of groundwater within those fill soils. Now I want to show you some examples of, what happens if we don't put all this stuff back, the typical kinds of things that we see. So with regard to water management, the biggest issue here is that roads, pipeline rights of way, and the pipeline trench itself can capture, concentrate, and divert water to areas that it would otherwise not be. And that's just a recipe for a problem. So, the idea behind water management is to make your pipeline right of way or your linear corridor project invisible to water flow, as if you were never there. The surface water runs off, goes off of it, and you are not capturing any kind of groundwater within your fills or your pipe ditch. This is a picture of a steep slope. Pipeline is oriented with the fall line of the slope. So we didn't have to have any kind of deep excavation cuts and fills here. But that doesn't necessarily get you out of the woods just from avoiding that kind of earthwork. Just on a steep slope with the fall line, your biggest risk here is that opened up corridor can now capture a lot of surface water runoff. It's going to flow down that right away a lot easier than the vegetated slope. And if you don't have good water breaks or water bars to divert that water runoff off of your right of way, you're going to have severe and mass erosion like we see here, up to and including exposure of the pipe. This is an example of a pipeline corridor down the fall line of a slope with adequate water bar construction. So I can't emphasize enough how important it is to get really good, effective water bars at appropriate spacing, which should be specified by the geotechnical engineer on the project, and is sometimes regulated by agencies. But the water bars are a critical part of risk reduction here. This is an example of a fill slope after they had restored the pipeline right away, put all their fills back. And obviously we have a water issue here. We had an accumulation of groundwater and potentially surface water, and some water controls would have been useful here. One of the things that also can affect our slope stability along our pipeline rights of way are temporary fills during the pipeline construction project. We see this frequently. Contractor finds a spoils area, designated area to stockpile spoils, and they can put a whole lot of material on the slope, load it up, and initiate a failure. Now, for the permanent fill slopes and restoration of the corridor, so what we're talking about, as I mentioned before, you typically have a cut fill prism put into your slope for pipeline construction. After that, you take your side cast fill after you've got your pipeline installed. And in this case, in this schematic, we're showing a pipeline installed on the outboard side of the right of way, which is not preferred. Because as you can see here in this example, it doesn't really get down into this more competent underlying bedrock or more stiff material. It's more close to the surface in that more marginally stable superficial colluvial material. But in any case, once you take this temporary fill and you put it back here, if you do not get that put back well, you are subject to that material failing. And under the best case scenario, it doesn't impact your pipeline. But even in that circumstance, it can mobilize downslope inner water body, and then you're looking at potentially fines and violations of state and federal environmental regulations and the Clean Water Act. And we have seen plenty of that with many of our clients. Now, under the worst case scenario, though, you can have this failure continue down through into those upper colluvial soils and impact your pipeline and potentially affect pipeline integrity. So, you know, these aren't large scale, deep-seated landslides that we're avoiding here or trying to mitigate against. You know, this is just your fill slope that you're putting back as part of your pipeline construction. And so this just underscores how important it is to get that done right. And so here's a few more examples of where you typically can have some problems just like that. We saw this one earlier, more saturated fill flowing out. You can see the headscarp up here of a fill slope that was constructed after pipeline restoration. Here's another one. This was probably a combination of some poor drainage control here and possibly inadequate compaction of your restoration fills. So with that, I want to talk about how we need to be placing these fills to hopefully ensure that they're going to remain stable in the long term. And so there's a few of the most common measures that you'll want to consider, and that's fundamentally having some form of drainage control where it's appropriate, integrating some subsurface drainage elements, whether that be like a blanket drain, a foot or so of well-drained rock before you start placing that side cast fill back in, or an interceptor drain on the cut slope, or both. Now, typically what you want to do in the upfront design of a project, when that route is being evaluated, your geotechnical engineer should be looking at the areas where you know we have concerns for the long-term stability of your fill slopes. You know, these side slope areas, and depending on the slope gradient, is going to potentially affect how many measures that you put into place to manage the stability of your fill. In addition to drain implementation, obviously compaction of the fill is a critical part of this. And that's one of the trickier parts of pipeline construction. Obviously, one of the most important things with fill placement and compaction is that you put it down in relatively thin lifts, typically 12 inches or less, and compact it in horizontal lifts. Now, getting adequate compaction is really the challenge, and measuring how well you're compacting your fill is the challenge. Now, historically with pipeline construction, documentation and control of your fill compaction is not a common thing to even think about. And it's because I think historically people have not looked at it as a realistic thing to be able to do. You're dealing with miles, tens of miles, or even hundreds of miles of pipeline corridor that may be constructed. And being out there with a nuclear density gauge and measuring, you know, your specific percent compaction relative to theoretical maximum is just not going to work. You have too much variability in the soil to get an accurate theoretical max through a Proctor test. You go out there with a nuclear density gauge, if you've specified something like a 90% compaction, your contractor is just not going to make the progress that you typically going to need to see if you've got somebody out there saying, oh, I'm sorry, you know, you've got 88 here, it's not 90, and they're out trying to moisture condition things, and it's just going to slow them down too much, and it really isn't practical. So what we're suggesting is, you know, don't throw the baby away with the bathwater. don't throw away the idea that we can get some kind of control on compaction of your backfill. It's really important that we address this. So what we recommend is a more qualitative approach to evaluating compaction and how well your material is being compacted. And that means visual observation by a trained professional that knows what they're looking at. Proof rolling, seeing the performance of that fill under the load of your compaction equipment or hauling and spreading equipment, and potentially probing it. So if you have a geotechnical representative out there and they're watching these lifts of fill go in and the stuff is pumping, you've got huge amounts of deflection and tire rutting, you're looking at material that's probably well wet of optimum. And there are things that you can do to address native soils that are wet of optimum. You can look at doing some lime amendment to try and dry it out a little bit more. And worst case scenario, if you can't dry it out so that it's workable and get reasonable compaction, you can look at then integrating the fill with some mechanical stabilization, like a geogrid or a geotextile fabric. And depending on how steep your slope is or your fill slope, that's going to influence whether or not you got to go to that next step. If you're looking at a 3-to-1 slope or gentler, okay, maybe we can get away with only a moderate level of compaction because the soil's too wet. But if you get upwards of a 2-to-1 slope or steeper, you're going to need that material to be pretty well compacted in order to remain stable in the long term. And so that would be an instance where you would want to have a backup plan if you cannot get adequate compaction. And that backup plan might be, like I say, integration of geogrid or geotextile into that fill to compensate for the fact that you're not getting adequate compaction. And at the end of the day, what we recommend is that you treat these geotechnical best management practices similar to like your typical erosion and sediment control BMPs, where you've got a trained individual on site that is assessing the various erosion and sediment control issues as they're encountered on a pipeline construction project, and they're picking which BMP to use. Hey, we want to have a silt fence here, we want to have some check dams there. They have a toolbox of different erosion and sediment control BMPs they can pick from depending on the kinds of challenges that they come across in the field. Well, we see the same thing being applicable for geotechnical considerations. So early on in the project, your geotechnical engineer can put together a toolbox of typical details and measures, specific drains that can be employed under specific circumstances, fill compaction methods, and get this into the plans and specs, and then have somebody out there prepared to implement these things in the field. So the takeaways here, in summary, upfront due diligence. You can really save a lot of headache by doing your due diligence and your desktop study and avoiding problems at the desktop stage. Then during construction, get your fills placed well, do the earthwork right, implement drainage controls. Preventative measures, it's going to save you a lot of time and money in the end. So with that, do we have any questions, April?
Yeah, we do, Trevor. Thank you. What is the typical side slope percentage that you should start at considering route changes in the design stage?
Well, our preference is that you avoid side slopes altogether if you can. However, really where we see where we have some concern is probably starting at a 3-to-1, roughly a 33% gradient. Less than a 3-to-1, a more gentle slope than a 3-to-1. It's pretty easy to construct a fill slope at that gradient that will likely remain stable, provided you don't have any serious focused water issues. So 3 to 1 is where we start getting concerned. 2 to 1 is probably where we would take it to more of a site-specific design. If you're on a side hill that's 2 to 1, that's where you want to be preparing some site-specific details and plans for how to restore that part of the right-of-way. But good question.
Awesome. And then how often are erosion or slope stability problems the result of inadequate initial investigation and poor routing decisions? You kind of alluded to the importance of that due diligence up front.
Yeah, a huge amount. I mean, it's probably more than not. And one thing I meant to bring up in the routing slide and analysis, those two that I was comparing, the one that was not routed to the terrain was following a power line corridor. And that's what we very commonly see. When pipelines are not routed to terrain effectively, it's usually because the owner operator is compelled in some way to follow an existing right of way, and oftentimes it's power lines. Well, power lines have the ability to span, they put their towers on ridge tops and they get to span all of this terrible terrain. Well, the pipeline cannot. And so the biggest problems that we have seen, I personally have seen on numerous pipeline projects, the ones that have gone the worst are ones that followed a power line corridor where they were not able to route it effectively to avoid side hills.
So that's it for the actually, one just came in. Hold that thought. How often do you see anchors and heavy-duty erosion control mat systems installed on the right-of-ways? Specifically, something like the, and I'm going to say this wrong, I'm going to just say it now, Propex Armor Max 75 SS system.
Yeah, so that, those types of systems are typically used when we're dealing with really steep slopes. Slopes that are steeper than 2 to 1 typically. That isn't, it's completely uncommon. I don't know, Andy, if you've got any experience with that, but that is something that may be employed on particularly steep slopes.
Yeah, it's really an erosion control measure, a really beefy erosion control measure. It can help stabilize the upper foot to 2 feet of the soil, but when we're talking about deeper landslides, these systems really don't help that much. It's really a superficial erosional issue.
Awesome. And Trevor, can you go to the last slide? I just thought I'd show this last slide has both Trevor and Andy's email addresses on it. If you have any follow-up questions after today's webinar, definitely reach out to them. They love it. And we'll definitely be sending a certificate of completion as well as a recording of today's webinar within the next 24 hours. So you can share it with your staff and you can also report it for PDHs. So with that, I don't see any other questions. Trevor and Andy, thank you so much for taking the time to share this information with the folks on the phone. And for those that joined us, Grady, Martin, Angela, I see all these wonderful names and folks that took the time to join us. So thank you so much. And we look forward to seeing you at our next webinar in Q3. We'll be in touch. Have a wonderful day.
Thanks, everybody.
Thank you.